Have you ever really looked at a coastline? I mean, really looked? The closer you get, the more jagged and complex it becomes. Or think about a tree, how its big branches split into smaller ones and those split into even smaller ones, repeating the same basic pattern. Well, today, we're diving deep into the hidden mathematics behind these beautiful, infinitely complex shapes. We're going to explore a brand new way to understand them.
And our guide for all of this is a fascinating scientific paper by S. Satin and A.D. Gangle. What they've done is pretty amazing. They've essentially created a new blueprint, a whole fresh set of tools to help us finally get a handle on how things move around in these incredibly intricate spaces.
But hang on, why do we even need new math tools in the first place? I mean, don't we have calculus? Well, to get why the old stuff doesn't quite work, we have to start with a classic puzzle. It seems super simple on the surface, but trust me, it's anything but.
Right. How long is the coastline of Britain? This is a famous paradox for a really good reason. If you take a giant ruler, say 100 kilometers long, and lay it along the coast, you'll get one answer. But what happens if you use a 1-meter ruler? Suddenly you can get into all the tiny little nooks and crannies, and your measurement gets way, way longer. So what if your ruler was infinitely small? The coastline would literally become infinitely long. It's pretty clear our standard way of measuring things just breaks down here.
And that, right there, is the very essence of a fractal. It's a shape that just keeps revealing more detail the closer you look, with patterns that repeat on smaller and smaller scales. You see them everywhere once you know what to look for. Coastlines, clouds, snowflakes, even the branching structure of our own lungs. They're all fractals. It turns out, nature is absolutely jam-packed with this kind of infinite complexity.
So, we've established we have these infinitely jagged, complex shapes all around us. But what happens when something tries to move along one of them? This is the huge challenge that the paper really digs into, shifting us from just looking at static shapes to understanding dynamic motion within them.
Think about it like this. Normal motion is like a car driving down a highway. It's smooth, it's predictable, and it follows all the laws of motion we learned in high school physics. But fractal motion? No. That's more like an ant trying to walk across a crumpled up piece of paper. It's a chaotic, jagged, unpredictable maze where all our standard rules and equations, they just don't really work anymore.
You know, this weird kind of movement actually has a scientific name. It's called anomalous diffusion. It's what happens when a particle's movement just doesn't scale up in that nice, clean, predictable way we'd expect. And this isn't just some abstract idea for a chalkboard. It happens in the real world all the time. The paper actually points to examples like gas wiggling its way through porous nanofibers or molecules trying to navigate the super crowded environment inside a living cell.
So, what do you do when your old trusted tools just can't handle this new bizarre terrain? Well, you have to invent new ones. And that is exactly what the authors of this paper did, and it's a pretty major breakthrough.
Okay, so their first huge innovation is something they call F-alpha calculus. The best way to think about it is like a whole new mathematical language. I mean, you wouldn't use a yardstick to measure an atom, right? In the same way, standard calculus was designed for smooth, gentle curves. F-alpha calculus, on the other hand, is custom-built from the ground up for the jagged, self-similar world of fractals.
And of course, if you've got a totally new way to measure distance on these crazy paths, you're going to need a new way to measure speed, too. That's where alpha velocity comes in. A normal speedometer in your car tells you how fast you're going down a smooth road. But alpha velocity? It's designed to measure how quickly a particle is actually making progress along a path that twists and turns on itself infinitely. It's a whole new definition of speed for a whole new kind of world.
Okay, so we've got the new tools to describe the fractal path itself, that's sorted, but what about the motion? In these kinds of systems, movement is almost always random. So how do you possibly build that randomness into a working model?
Well, for more than 100 years, physicists have had a really powerful tool for exactly this problem. It's called the Langevin equation. You've probably heard of the classic example, Brownian motion. It's that random zigzagging dance of a speck of pollen and a drop of water, getting bumped around by trillions of invisible water molecules. The Langevin equation is basically the math that describes that dance. Conceptually, it's actually pretty simple when you break it down. You start with your particle. Then you add some kind of steady force that's pushing it in a general direction. But then, and this is the key, you layer on a whole series of random kicks from its surroundings. The particle's final path is just the outcome of this constant tug-of-war between the steady push and all that random noise. So here's where it all comes together. This is the crucial point. We've got this brand new, purpose-built toolkit for the fractal space, and we have this classic, time-tested blueprint for describing the randomness.
The absolute genius of this paper is that it finally brings these two powerful ideas together into one unified theory. This is really the heart of their entire contribution. They essentially gave the old Langevin equation a massive upgrade. They took its solid, reliable framework for describing randomness, and they plugged in their new tools, the F-alpha calculus and alpha velocity, to make the whole thing work not on a simple smooth line, but on an insanely complex, twisting fractal curve.
And this right here is the aha moment. This is how they knew they were onto something real. So how did they prove that their new, souped-up method was actually correct? Well, they showed that for a specific, well-understood type of randomness, their new Langevin method gave them the exact same answer as a completely different but already established theory. As the paper puts it, the two approaches are equivalent. This was the mathematical mic drop, the proof that their new toolkit wasn't just a clever idea, it was actually correct.
All right, so this is all really cool theoretical work, but let's get down to it. What's the point? Why does figuring out how to model motion on a fractal actually matter in the real world?
It matters because these fractal structures are, quite literally, everywhere. The source material itself points to some absolutely critical applications. We're talking about understanding how gas diffuses through high-tech filtering nanofibers, how proteins and drugs move around inside our own cells, the fundamental structure of plastics and polymers, and even modeling how tiny fractal cracks can grow and lead to catastrophic failure in things like bridges and airplanes. This isn't just an abstract exercise. This is fundamental to biology, to engineering, to just about everything.
And that kind of leaves us with a really fascinating final thought, doesn't it? By creating this new mathematical lens, these researchers were able to see and describe a world that was always there, but was basically invisible to us before. It really makes you wonder, what other complex, seemingly chaotic patterns all around us, maybe in our economy, in ecology, even in our social networks, are just sitting there waiting for someone to invent the right set of tools to finally bring them into focus? What else is out there, just waiting to be discovered?